Hello to this presentation. This is Elina, and here with me is Muhammad, and this is for the course Renewable Energy System, our final project. The title of our project is Design and Simulation of a Solar-Powered Reverse Osmosis Drinking Water System in Dubai. Can you please move on to the next slide? Perfect. All right, let's start with the introduction. First of all, Dubai faces significant water scarcity and currently relies on fossil fuel-powered desalination, which is energy intensive and contributes to greenhouse gas emissions. So in this study, we explore using solar-powered reverse osmosis, so RO systems, integrated with photovoltaic panels, energy storage and control systems to sustainable supply water to a 7-bedroom villa in a Blue Waters Island, Dubai. RO technology effectively purifies seawater by removing salts and impurities, but requires substantial energy, making it well suited for pairing with renewable sources like solar power. Dubai has a high solar irradiance, and its stable climate makes PV systems an ideal choice for reducing both carbon emissions and long-term energy costs while enhancing water independence. In this study, we use Homer Pro and MATLAB/Simulink to model and optimize the system for energy reliability, cost effectiveness, and performance under varying conditions, including cloudy weather and nighttime. Let's move on.
So I will now explain a little bit about the reverse osmosis system configuration. So the reverse osmosis system starts with a semi-permeable membrane, which aims to remove all the salt, ions, molecules, and large particulates from seawater and making it suitable for drinking. So it might not have one membrane, there might be multiple different stages of membranes involved so that at the end stage we get the pure fresh water. So at the first stage, we do the pre-filtration, which aims to remove all the large particulates, and it involves pressurizing the water through that membrane. And we also have to store the filtered water separately from the containments. So as we have located we have selected such a site which is near the sea, so we will be able to extract the seawater and pump it directly into the reverse osmosis system. So the reverse osmosis system we have selected is capable of supplying 1,000 gallons per day, and thus it would satisfy our demand for around 800 gallons. So the system that we have selected is the Flexion ED1000 which features a lightweight, compact design and is a low operating and maintenance cost. On the right side here, we have a block diagram explaining just a little bit about how a reverse osmosis system works. So we start with the electric supply, which is supplied to the inverter, and the inverter supplies power to the RO system. So the water, which we will be getting from the seawater, it goes into the brine storage tank, and then it passes through the reverse osmosis system. So at one place we get all the containments, all the waste material, and at the other side we can get the fresh water. So these are some key elements that are involved in designing our reverse osmosis system. So we start with the PV solar panels that are going to be used for extracting power from sunlight. Then we have a backup battery bank, which will enable our system to be powered during the night time when there's no sunlight involved. Can also power the system during cloudy weather when there's not enough sunlight. And at the last, we all have the reverse osmosis plant. We also have some control systems involved like MPPT, which is a maximum power point tracking, the battery charge controller, and the DC-DC converter. To meet the reverse osmosis system's 1.65 power need, we have designed a 2 kilowatt PV system in Simulink, and we did the simulation with different scenarios to show that it does work in different scenarios. The key components all included a Fronius Simo solar system in Homer, a Cybo Energy off-grid twin pack inverter for power conversion, and an MPPT charge controller to regulate energy flow and prevent overcharging. A boost converter regulated by the MPPT controller using pulse signals to an IGBT switch stabilizes voltage levels for both the battery bank and RO unit, optimizing overall system efficiency and performance under fluctuating solar conditions. On the right side, we have a block diagram explaining how does our system would work. So initially, we are getting sunlight from the solar panel. The solar panel is generating power, and that is being optimized by the MPPT controller. After the MPPT controller, we have a boost converter that is supplying power to the battery bank. And from the battery bank, we have a bus that is supplying power directly to our RO load. So this is the Homer Pro schematic, which will be explained by Lena.
Yes, so as mentioned before, we simulated the system in Homer Pro to evaluate the technical feasibility and optimal system configuration. On the right, we have the system schematic in Homer Pro. And basically, the system components are the solar PV array, which is 4.5 kilowatts, then the battery bank, inverter, and the domestic water, the load. The load profile is that the daily demand is 21.64 kilowatt hours. The solar resource for our location downloaded from Homer was 5.75 kilowatt hours per square meter per day. And the battery has 12 hours autonomy with 90% round trip efficiency. And the system efficiency was MPPT 90%. But let's move on to the Homer Pro results in the next slide. Yes, so let's start with the performance highlights. The PV system met 100% of energy demand year-round. The battery bank, we had 4 units, ensured overnight autonomy, and no unmet load or capacity shortage was in the system. Renewable fraction was 100%. The LCOE reduced over 25 years due to no fuel and low maintenance. The batteries were the largest capital cost share. The energy production stable due to high solar irradiance in Dubai. And yes, here on the right, we have the picture of Homer Pro and the simulation results showing the energy production of the solar panels. Let's move on.
So now I'll cover briefly about the dynamic modeling and simulating. So as we discussed earlier that our plant consumes 1.65 kilowatt, but we have designed a simulation based on 2 kilowatt peak load factoring in efficiency losses. The figure shows the simulating schematic. And we have started here from the solar PV panel, and then as we can trace the power, it's going into the MPPT controller at the top. And then from the MPPT controller, the power goes to the battery. And from the battery, the power goes to the reverse osmosis plant at the last, which is the load. So these are the results. The figure below shows the waveform of the radiance and temperature. The radiance increases as day progresses and finally drops to zero, indicating nighttime. This is the output waveforms for the power. We can see that as the radiance and temperature increases, the power increases and goes to a maximum value of approximately 2 kilowatts. Now, this is a brief introduction about the control system which we have used to optimize the power consumption of the reverse osmosis system. So the main power consuming components is the motor that pumps the water through the filtration membranes. So in order to simulate that motor, we have selected a brushless DC motor to represent the pump, and it's also it's preferred in industries because of its efficiency and its electronically commutated design. The motor's motion is controlled by sensors, providing rotor position data for precise and efficient operation. So, in order to control a three-phase inverter, we have to control the switching of three pairs of inverter switches, which are generally MOSFETs. The figure below shows the complete control system simulating schematic, and we can see that the AH and AL represents the high and the low. And then we can see that these are all being controlled by their angular position. This is a brief information about the protection system which we have used. So if you consider for Dubai, there are environmental risks like sandstorms, high temperatures. So in order to protect the system, we have to introduce surge protection devices, grounding, overcurrent, and voltage protection. In order to combat sandstorms, we might also need to clean the solar panels like very often. The main components which need protection are inverter, battery bank, and control circuitry. The figure on the right shows a brief block diagram of the protection system. How would we use the different metrics in order to protect our reverse osmosis system? So we are taking into account the EMF, we are taking into account the voltage, we are taking into account the temperature, so that if there's any irregularity, we can ensure that the system trips and our system is saved. So the project focused on powering a reverse osmosis system using solar energy with technical feasibility verified through simulations at Homer and MATLAB. Custom control system was designed to manage motor speed via switch combinations, and protective measures were implemented using discrete wavelets to guard against overvoltage and overcurrent. Surge protection devices are incorporated to safeguard sensitive components from voltage spikes, enhancing system reliability and safety. While the system involves high initial investment, it is ideal for regions with abundant sunlight and access to seawater, making it a practical solution for remote or off-grid locations. Future work includes developing a physical hardware prototype to validate the functionality of the design control system in real-world conditions. Thank you.
Thank you.